Where's the raw data available?
It's a journal called PeerJ.
So PeerJ hosts the data. It's not some other site of hosting.
PeerJ published data paper. The data itself is hosted at, I think, Zenodo or something. I don't know.
Where's the data hosted?
Zenodo.
Zenodo?
That one is in PeerJ.
Okay. All right. Great. Hey, guys. Our next talk is by Patrick Holmes and Shannon Danforth, and I'll let you guys introduce your talk.
Okay. Hey, everyone. I'm Shannon Danforth.
Patrick Holmes.
And this is our work from Rome Lab at the University of Michigan in collaboration with Talia Moore and Ram Vasudevan. So recall from our latest choreographed music video that we're interested in predicting instability during motion, and in particular during sit-to-stand. Best Video Award. So here's an example of an individual's nominal sit-to-stand motion under a specific control strategy. We can build some model of this person's motion, and for the purpose of this cartoon, we'll lump all the model states together and plot them over time. So under this control strategy, there are certain perturbations, like the blue force shown here, that the individual can successfully recover from. But other perturbations are too large, and so the individual may switch to taking a step. And if the force is applied backwards, the subject may have to sit back down. So we're interested in computing an object that can predict when a sit or step will occur in order for a subject to recover their balance. We call this object the stability basin, and we've successfully computed it in collaboration with Victor Shia. But today, we'll talk about our validation of the stability basin, where we perturb subjects in a way that causes them to take steps or sit back down, and then check if the stability basin predicted these instances. So our sit-to-stand experiment involved 11 healthy subjects, age 18 to 32. First, subjects performed 5 nominal trials from a comfortable foot position using their natural strategy. Next, they shifted their feet forwards and then backwards in 2-inch increments. And the third type of trial introduced pulls from a motor-driven cable, both forwards and backwards, and limited to the sagittal plane.
All right, so I'll walk you through our pipeline for computing the stability basin. First, we start with motion capture data, and we use that to build a telescoping inverted pendulum model of the subject's motion. This model has 4 states, which are the horizontal and vertical positions and velocities of the center of mass. And it has 2 inputs, which are the horizontal and vertical forces on the center of mass, as well as control affine dynamics. We use inverse dynamics to compute the inputs for every observed successful trial. Now, these inputs are a function of time, but they're also a function of state, which I'll just lump together into a single dimension for this cartoon. We then bound the inputs by looking at each slice in time, and then constructing 2 linear functions of state that upper and lower bound the observed inputs. Next, we create a standing set from the final states of all of the observed successful trials. On the right-hand side here, I plotted the horizontal states versus time, and on the left-hand side, the vertical states versus time. And finally, we use a reachability toolbox called Cora to backpropagate the standing set under our model's dynamics and our input bounds. And this is the stability basin. So this is describing the set of states through time that can arrive at the standing set without exceeding the input bounds that we specified. So now we want to verify that the stability basin accurately predicts whether a trial will be successful or unsuccessful. All these blue trajectories remain inside the basin, and so we accurately classify them as successful. In this trial, the subject was pulled forwards and ended up taking a step. And here, the trajectory exits the basin, so the basin accurately classifies it as unsuccessful before the step occurs. And in this trial, similarly, the subject was pulled backwards and had to sit back down. And again, the trajectory exits the basin.
Okay, so now I'll briefly talk about our validation process while reporting the results for all 11 subjects. So in order to avoid training and testing on the same data, we checked the successful trials on a leave one out basis. Next, for each subject, we take all of their successful trials and then check the unsuccessful trials. So we're checking that step trajectories exit the basin before the subject begins to lift their foot, and sit trials exit the basin before the subject's center of mass reverses direction. So as you can see, our method is very accurate for successful trials and sit trials, but the prediction rate is lower for trials where a step occurred. So our future work in validation will focus on reducing or improving this step prediction rate by reducing the conservativeness of our method and experimenting with different models for sit-to-stand. We'd like to thank Victor Xia for his advice, Art Kuo and Xiaoyu Fu for helping us collect our data and our test subjects. Thanks.
That was amazing. That 5-minute talk took 4 minutes and 47 seconds. Give him an extra few seconds of applause. Okay, they have 1 minute for questions. Or longer if they're good questions. Chris. Sorry, guys.
So the interesting thing for sit-to-stand is that you're going into, from a robotics point of view, a singularity, which actually greatly simplifies control. And I'm wondering if you see the effects of that when you look at sort of sensitivity to perturbations early on versus later on.
By singularity, do you mean like the joints are fully extended?
Yes.
No, we haven't really looked at that. But it's an interesting question. We definitely want to look at a triple pendulum model and then see if we could perform the same analysis, but we haven't done that yet.
Chris, could you just explain what you mean by greatly simplifies control?
So as you stand up, you lose the ability to control for vertical perturbations, and you now have all sorts of control authority for fore-aft perturbations. And if you can get energy going vertically, then it just magically disappears and simplifies the control problem.
Is there a rebuttal to that?
That video playing about sit-to-stand seems to be a rebuttal to this remark. Like they're all walking with bent legs.
There's a video playing above your head, Manoj says, that is your rebuttal.
Which one? Let's try.
Can you explain what you mean, Manoj?
Well, you say it simplifies control. Why are they all walking with bent legs?
Because robotics has been barking up the logical wrong tree for decades.
So what just happened there was one of the things the moderator tried to do is like not just go in order, but to connect some people who might disagree with each other. Okay, so this is in order. Go ahead.
Hi, this is Mohammed from Rice University. So I have a question about, writing or modeling it in a way that is just an inverted pendulum with a point mass. So how about angular effects? Specifically with sit-to-stand. So how does the model recognize the difference between like a quasi-static sit-to-stand, which happens in elderly, rather than just an upright kind of sit-to-stand with high acceleration? Specifically angular accelerations of the torso. Thanks.
Totally. Good question. Right now it doesn't. So with a point mass, there's no ability to take into account, like, especially during sit-to-stand at the beginning, you're building up a lot of angular momentum with your torso, and we don't really have a way to account for that right now.
Yeah, and we could also throw in that we did perform this experiment, having our subjects do quasi-static, their natural strategy, and the momentum transfer strategy. And these results are just the subject's natural strategy. So yeah, we still have to look at the other two.
All the way back.
So how do you accurately represent the input limitations on the simple model, given the large kinematic range you're moving through?
You mean with regards to those input bounds that I showed?
For the center of mass models, you're trying to compute reachability basins, right? So you need to have input limitations on your, I think they were like X and Y forces.
Right.
Those would seem to be very configuration dependent.
Right. So we have the bounds are actually a linear function of state, but they're just tight enough to include all of the observed successful inputs. They're just linear functions.
So not even time varying.
They're time varying. We solve for them at each time slice, and at each slice in time, we use like a different linear function.
So you said that you could predict that people are going to take a step or sit down before the center of mass directly changes stuff, right? So if you look at people's EMGs or something, do you think that people predict whether they're going to fall before your model predicts? Like, do they go unstable based on your model and predict it later or before?
Yeah.
That's a really good question, and we did also collect EMG data at our experiment that we have
Not looked
yet
at it,
to delve into. But yeah, that's a very good question.
Yeah, I think the person will probably know that they have to step before our model will predict it, and you could probably see that with EMGs on their legs.
I don't understand the nature of those sort of externally grounded U's. Like, nobody's like pulling on the center of mass, so I don't quite understand how, maybe the model kind of gives good bounds, but do you think it's actually a biophysically realistic model?
You mean in like real life situations, no one will be pulling on the center of mass?
Well, nobody's
or-
out there pulling a U-X and a UY on the center of mass.
Yeah.
It's
Yeah.
doesn't seem to relate to the biomechanics directly.
I guess our main point of this validation was we've already been able to construct the stability basin. Now we'll perturb subjects in a way that causes their trajectories to leave the basin and see if they then take a step or sit back down. So those perturbations could happen other ways. You know, people aren't going to get pulled by cables in real life, hopefully. But we think that if their trajectory exited the basin from a different way, we'd still predict it would take a step or sit.
Okay, thanks speakers.